Hi all, so here's some quick video to give you some idea about the type of questions you'll be asked on the exam. Now here's the big caveat that I'll give you. When you take the exam this semester, you are going to be taking it from a test bank, which means there's a whole group of questions, and some of those questions will be pulled off by the testing software and given to you, and I can't predict which questions you're actually going to get. The exam that I'm going through here real quick is one that I gave in class in fall of 2019, and during that time there were just a fixed number of questions. So can't guarantee it'll look like this, but you'll get an idea of different types of questions that may be asked. So this was the first question in the exam. You got these two forces acting in a 3D um, manner. It asks you to kind of lead you through the problem. It's actually kind of laid out kind of nicely in that case. So it asks you to find the two forces in Cartesian form, rectangular form, right? The same thing. Find the resultant force. And then the last part is doing a dot product, finding a projection of a force along one of the two cables. So what do we do with 3D problems, right? We know most of the time we start with identifying the uh, points. So in this case, identified points A, B, and C, right? So I need to define my force, well, both my forces, my F1 and my F2, based upon I have a direction, a line of action, and I have a force. So remember the process that find a position vector, take and divide that by its magnitude to get a unit vector, multiply the unit vector by the force given, and you will get a force along a line of action. So in this case, I did this for the first one. F1 acts along the line AB, right? And then the other one acts along the line AC. And you can see the steps that I did to do that here. Same thing, repeated the same thing. This one acts along AC. That gives us F2. Again, these are both in Cartesian or rectangular form, right? X, Y, and Z pieces. So last slide, pretty simple for this problem. Gives us the resultant force, right? So we combine those two forces together, we get the resultant force. And then we wanted to find the projection along line AC for force 1. So we found the force 1 before, a couple slides back there. We took and we dot product that with a unit vector that goes along AC, which you'll see that at the last slide. Right? You do the dot product and you get the final answer there of 56.3 newtons. There's problem 1 from that former exam. So problem 2 is, this is similar to one of the quizzes that we had. So go back and take a look at that solution, but in this case, instead of a weight, there's somebody's hand pulling down, right? So you're substituting a crate for a hand, right? In this case, we've got a hand pulling down. It's pulling down with 80 pounds of force, and it causes an angle. That unknown angle, theta, is that's labeled there, is 60 degrees, is known. You have the length of the cord, AB, and you have the spring constant. Right, and they want to find out what the unstretched length of the spring is. So in this case here, the first trick you got to realize is this isn't a right triangle. So since it isn't a right triangle, I've drawn out a triangle with everything that we know. Right, we've got that known angle that was told to us is 60. We know how long that two of the three sides are. So we use law of cosines to find the unknown side, and then we use law of sines to find that old unknown angle, which I've labeled as phi here. Right? We need that information so that we can draw the free body diagram to do this problem. So I've done that. I didn't put the angle there, but you can see, right, I got the sine of phi equals 0.5, which is a 30-degree angle, as you can see here. Right, so I took that information, I plugged it into my free body diagram. I've got an unknown tension, I've got an unknown force, and I've got the two angles, and I've got the weight pulling down. In this case, it's somebody's hand rather than the crate. Doesn't make any difference. Again, in English units, 80 pounds force, 80 pounds mass are the same on Earth. So I sum my forces in the x direction, set it to equal, sum my forces in the y direction, set it to equal. I've got two equations with two unknowns. Right, all I actually need to solve for is the force in the spring, but you can see I solve for both of them there. Right. We use that information to go back to, remember we had this formula, the force of the spring equals K times S. K was given to us in the problem. We found, right, S is the difference, it's the stretched length. So it's the difference of the length after it's stretched minus its original length. Right? That's how long it is stretched. So with that information, we can plug in all our knowns and we solve for our unstretched length, which is 2.66 feet in this lateral. So third problem, this was probably the trickiest problem, to be quite frank, on the exam. And it's probably the trickiest problem because, again, recognize it's a 3D problem. So we need to identify those points A and B, and they're a little hard to see. You'll see on the next slide, I tried to sketch out how I found those two, and hopefully it's clear to you as you look at it. Because what are you trying to do? There's a strut that's exerting a force, and you want to find what that force exerts on point B. No, they tell you the force that exerts on point B, and you want to determine the moment of this force around point O. So what do you need? You need a position vector from point O to the line of action, and you need to take that force and express it as a vector in the 3D space. Right, so you need to identify O, which is real easy, and you need to identify points A and point B so that you can define those two vectors. So you'll notice here O is at the origin, right? And I've tried to draw, so there's a triangle that's shown on that. I can't go backwards when I'm doing this, but there's a triangle that was shown on that picture that we just looked at. And I've tried to sketch out the Y and the Z portions here to show you where B and where A are. So with that information, you can see that I found the position for A and for B. Right, so I use that information as I've got here to find my position vector, right, from the origin to point B. So that's the position vector that I will cross with the force to find the moment. And of course, we got to express the force as a vector. So remember how to express a force as a vector is you find a position vector, find the magnitude of that position vector, divide each piece by the magnitude of the position vector, which gives us a unit vector, multiplied by the force given, and now we have the force here in vector form. So I've got the force, I've got the position vector, I can do the cross product. Here's the odd thing here, this problem was actually taken directly from the textbook, and I got the top answer, and I must have done some crazy rounding, but I got the top answer. The solution manual has the bottom answer. I don't remember I don't remember if I did crazy rounding or if they just did something incorrect, but those were the answers we got. So that's the process. That's the problem for the third problem that was on that exam. The fourth problem on the exam was essentially a chapter 4 problem. So what you're trying to do, this is further simplification in this case, right? We've got a beam that's loaded with a moment. It's loaded with a distributed load, and it's loaded with a force acting upon one end. And what they want you to do is find an equivalent force and figure out how far it needs to be from the end of the beam to give you the same force of all these things acting upon it. So this is similar to one from the textbook. In the textbook, that extra force is acting straight down, and I nicely put it at an angle to complicate things. So the way I did this problem first is I took and I resolved that 25 kilonewtons into an X and Y component, which you can see there. And I took the two distributed loads and I simplified them, right? So you can simplify distributed loads to point loads by taking 1/2 base times height for the magnitude, and they're always, that equivalent force is always 1/3 from the base. So I've labeled here the ends, and I've labeled everything, made sure to label everything to the side that I ultimately want to find the equivalent force from. So what hopefully you'll notice here, right, is we're going to need to find a force and we're going to need to find a moment. So the two distributed loads, those pieces will contribute to a moment at point O. The free moment will obviously gives us a moment at point O. The force that's on the end of the beam, right, the X piece goes right through point O, so it has no moment. So it's only the Y piece that contributes to the moment. So you'll see the way I did this problem is I solved for my equivalent Y force. Right, the Y piece is the only thing that contributes to the moment. So you can see I've got my moment equation written down underneath there, right? And for my moment equation, I've got the free moment, I've got the pieces of the other forces, only the Y force from the one at the far end. With that information, I found the equivalent moment, right? And then remember that force times distance equals moment. So I've got the free moment is the force. The Y piece is, the free moment is the moment there. The Y piece is the force, and I can solve for the distance, which comes out to 17.77, which interestingly enough, right, is off the beam. Hopefully you recognize that. The equivalent force, though, is not just the Y piece, right? The equivalent force will be made up of both the X and the Y piece. So the minus 12.5, there's only one X piece, right? That force that's acting on the end has an X component and a Y component. The rest of them are all purely Y components in that case. So I have the X, the Y piece. I bring those back into polar or vector form, and I got a force at an angle, right? That's 67.9 kilonewtons at minus 101 degrees. If you put that at 17.77 feet from, or meters, I'm sorry, from point O, then you will have an equivalent system further reduced. So there you go. That was an example for exam 1 from a past exam that I gave in class.